about RSqueak, which is also a VM to run, well, it's kind of, the idea is to be fairly drop-in compatible to Cog VM, but it's not to be confused with a production-ready VM in any way. It's a research experiment. It's a teaching vehicle for us, and it's more of a kind of vehicle for us to explore what kind of JIT optimizations are possible and how far we can push some things, and then kind of use that, what we learn also to kind of feed back into the Cog VM, into Disper, and maybe into Sister, and kind of discover optimization potential in that way. So I don't have a presentation prepared as there's a proper high-level presentation later this afternoon at the IWST workshop. And this here is more of an exploration of the code base. And basically for people who might in the future be interested in how we do some optimizations or some, like how we do some architectural decisions, to see if they want to get inspired by that. So the code is all up on GitHub, and there's bundles to download, pre-built binaries for x86, 64 and 32 bits, and for ARM. The ARM binaries, they do run on the Raspberry Pi, although I would not recommend running them on the Raspberry Pi 1, because our goal has been to explore some performance stuff, not optimized for memory requirements. So loading a 40 megabyte image, we use about 500 megs of RAM. That is without any JIT compiled code. So if you run this on a small Raspberry Pi, you're not going to get very far. Because we're exploring performance, we have set up this benchmarking website. The website is just stolen from the PyPy project. It's just every night we check the open Smalltalk VM repository and the RSqueak VM repository for new commits that are green, and then we start a new benchmark run with a bunch of benchmarks that we collected from mailing lists and different other projects that kind of stuff is mine. Yeah, and then we get these nice graphs where we can see how the performance behaves over time. And actually, sometimes it's nice to see that when Elliot or somebody else writes on the VMdev mailing list about some optimization they did for maybe floats, and then go to this website and you actually see a drop in the time it takes to run the float benchmarks. It's really nice to be able to see that. And yeah, we're using this to kind of track where we are with respect to the Cog VM. And what I wanted to show here, just really quickly, is let's take these two. So this is this one. This is, let's see if I can do it in person. So this is normalized to 32-bit Cog, the runtime. So less is better. This is runtime for the benchmarks. Less is better. This is the runtime on various benchmarks that we, Blue, have in comparison normalized to the Cog VM. So you can see that there's a bunch of things where we're like, how much? 50 times slower. But there are also a bunch of things where we're, like Delta Blue, for example, if we turn this normalization around, where Cog is actually 80 times slower in this particular example. So, and if we don't normalize kind of the general gist, unfortunately there's some really large numbers here, but the general gist that we often see, the pattern is that our optimizations are really vary wildly, the performance of them varies wildly across all over the place, and whereas Cog has more kind of a fairly reliable, stable performance baseline, we can be much faster or much slower. So that's also what I mean with this is not to be confused with a production VM in any way. It's purely research. Okay, the VM also runs. I wanted to run it real quick. And unfortunately, this isn't my main development machine for this VM, so this is running on Windows. Actually, this is supposed to print the Squeak mouse to the terminal, but Windows terminals apparently don't do UTF-8 very well, so you get that other thing instead. And why are we printing this? Because as you could see, I started the VM, and we actually have to load up the image, because we're treating the image as just an opaque format that you have to parse and read in and then convert into our representation of the object space. But we want to be binary compatible with the image, so that's why we have this startup time to read the image and fix everything up.
And looking at the Squeak mouse is much more fun than
yes, exactly. Yeah. So this is running in RSqueak, and you can see from the delays that the JIT really takes a while to warm up. Why are these delays when interacting with the UI? Well, we don't have a bitblip plugin. We don't have a balloon plugin to render anything. What we're doing is we are running the slang code whenever the bitblip primitive would be called. We check in the image. We have some code in the VM that checks, oh, is the VM maker loaded in the image? Then let's just kick off the simulation just for this one primitive call. And there's some overhead involved in that, and because there's very many methods, it takes a while for the JIT to warm up. But what we can do is, if I open this up again, oh no, actually that's too primitive. So, and it's opening. So this is, which one do I want? I think I want this one. So here, this is part of the interpreter simulation in the VM maker, and I'm not going to put a hold in there because then my image just freezes. But let's do a hold once, and now I've changed the method that is core to the rendering, so I've again blown some of the JIT caches, so we need to warm up again. But just to prove to you that we're actually running this simulation, I do this, and we get a debugger in somewhere in like, okay, the graph board copy bits, and then magically, rather than call copy bits, it goes to simulate primitive and ends up in the primitive copy bits. Right, what else did I want to show? Oh yes, one other thing that was interesting is you can see warm-up. So for bitblit stuff, we're about maybe 10 to 20 times slower usually in the benchmarks. In actual use, it's kind of, it feels more like about 10 times slower, and then when I open the frame rate more, that's about the kind of the gist that I get. But Balloon is about, we had done a paper about that, is about 500 times slower than using the C plugin. And when I click on this About Squeak button, what will happen is, I'm just going to click it because it takes a while anyway. What happens is it's trying to render true type fonts with alpha blending and stuff, and it needs Balloon to do this. So this is why, rather than instantly coming up with a bit of text, it just took literally 5 seconds to open up this thing. And then when I open something that has lots of text in it, like a contributors list, I'm waiting again. And maybe let's open a frame rate morph, just to give you a feeling for, because I guess you can't see very well how sluggish this feels. So, yeah, so that's about 40 frames per second. Oh, and because Clément was just saying about GC pauses in the UI sometimes, we have many more GC pauses because we generate, on every copy bit, we generate so many objects. We have really bad GC pauses. This is why you see the frame rate varying between 40 frames and 20 frames per second. Because we're generating points, millions and millions of points on every draw operation. And when I start like scrolling through this, frame rate drops to 3 frames per second, 5, 4, and it gets a little bit better after. So I once tried this to sit like this, scrolling up and down for 10 minutes, and it actually does get a little bit better. But our warm-up time is very, very, very long for these kind of things. Okay, so I wanted to switch to the code and show you a little bit of how the code is structured in the system and how I would develop things. So RSqueak is written in RPython, which was heavily inspired by Slang. And in the same vein, it looks like ordinary Python, but it's a restricted subset, and the restrictions are kind of fuzzy. The RPython is, by definition, everything that can be translated through the RPython toolchain. And the RPython toolchain does a whole program analysis to figure out all the types and what kind of methods it has to generate in C, which is also why. So on the one hand, this means that in RPython we are much more flexible than in Slang. You have actual objects, actual polymorphic dispatch, all that kind of stuff. But for generating C code, we have to do whole program analysis every time. So as the VM grows, translation times will only go up. And right now on this machine, it takes me about 10 to 12 minutes to compile the VM. And for PyPy people, this is even worse. It used to be 4 hours, now it's down to 30 minutes for them, but still. So what PyPy people do, and what we have adapted, is extensively write tests rather than translate the VM all the time. And the nice thing about this is that we have a fairly good test coverage. It's on the web page. It says about 50%, but that's only measured on OS 10, so that's not kind of measuring the code that's only run on Linux or Windows. And the other thing is that this way we can we've really taken the time to test tiny bits of the VM. Every primitive has a separate test case. And because this VM is mainly intended for teaching, this is very useful when we give it to students in kind of introductory VM courses, because then you give them this VM and they've never worked on a virtual machine before, but you can just kind of tell them to go ahead, run some tests, play around a little bit, and they have lots of tests to see if stuff breaks. So. So I wanted to start with this. We heard this morning also about how the object space is at the core of kind of what you're running when you run the image. By kind of pretty much all RPython-based VMs have a class 1 object space, just convention, and we do as well. That usually has a singleton instance, and that has stuff like lots and lots of, for us, config options, and then it has the class tables, global class tables, and it has references to the special objects array and nil and true and all these things, and it has wrapping methods for converting back and forth between Smalltalk objects and Python objects. Okay, well, so maybe I should. So the way this is structured is we have the object space, and that is referenced by an interpreter, and the only thing the interpreter does, it just has one core method, which is we call it stack frame. It should really just be interpret, and that is implementing the bytecode loop. So this is the interpreter is just doing the bytecode loop, and it's using the object space in the loop to just kind of get at objects and wrap and unwrap Smalltalk objects and Python objects, and then operate in Python world and then wrap them back into Smalltalk objects. And the kind of objects we have are all we call them models, and they all inherit from W object. Now W object is a wrapped object. The W is a convention to denote a Python level object that refers directly to a Smalltalk object. So W object is a Smalltalk object, and then there are subclasses of W objects that kind of mimic the most important parts of the Smalltalk object hierarchy. So we have W small integer, W float, and then W pointers objects to represent all other pointers objects, and W words objects for those. And so these W objects, they are simply boxing Smalltalk objects, and we only do boxing. We don't do integer tagging in RSqueak. We don't tag anything. Everything's boxed, and that's part of an experiment to kind of see how good we can get the inlining and the JIT to remove the allocations of small integers, for example, and actually works quite well. And then there's a parallel hierarchy. So here are all the models. And then there's a parallel hierarchy that's a shadow. And I said in the beginning, we're not interpreting the image directly, we're actually loading the image and converting it into our own representation, and that's what the shadow hierarchy is for. So classes have special shadows that represent kind of the class header differently for us. The class header is really this 264-bit words thing that with some bits set to represent different things in the class, and we just like pull all of that out, and everything gets its own 64-bit word. So classes for us in memory are much bigger, but we think it's for students it's a much easier representation. And then other shadows are more simplistic. They simply kind of include an array, and then there's pointers in there. But the nice thing is that we can use we can evolve the shadow hierarchy fairly independently from the W object hierarchy, and we can use the shadow hierarchy to optimize the representation of objects even at runtime. So when we find a homogeneous object, like for example points, where usually there's only 2 fields and those are usually integers, we're not going to allocate an array that has 2 pointers to 2 box integers. Instead, we realize, points usually only have 2 integers, so we're going to optimistically allocate an array that holds simply integers and plug integers in there and only de-optimize this representation if somebody stores something else into a pointer. And actually, for quite a lot of things, that actually works pretty well, because we found that if you, even in just an ordinary image, if you take a random point and start to mutate it and put plug characters in there or something, things will break anyway. So often this is quite a useful optimization, kind of the store syncing. What I wanted to do is show you kind of the process that we go through when we want to implement, or maybe not, let's do something else first. So I've been talking about the boxed integers and how we're not losing much performance. PyPy has a facility to print out the generated intermediate representation that PyPy uses to create assembler from JIT code, when it JITs code. This is all very Python-ish development, so you're using text editors and kind of environment variables, but you can set environment variables kind of ask to tell the VM, whenever you're JITting something, please write it into a file so I can later review that. And what I wanted to do is just run maybe a small integer benchmark, and then we can look at the generated JIT code and see kind of what comes out of the what happens to the allocations and all that.
And is that bench fit?
What?
Is that bench fit?
I was just going to use a simple integer loop that sums up some integers. Bench fit is special in a way because it's recursive, and what the JIT is going to do, it's going to unroll the recursion to a certain point, and then I wasn't going to use that because it's a bit harder to explain. Let's do. Oh, I have a mouse. Wow. And let's run Oh, so this, by the way, this benchmark runner thing, this is what's running the benchmarks also on the speak.squeak.org website. It's based on some work done by Stefan Mahr, who himself then based it on a paper, rigorous benchmarking in reasonable time. And the benchmarker attempts to run benchmarks often enough to have fairly, to be fairly sure about the results, but not so often that it takes ages. But because we're only interested in the JIT log, it doesn't really matter how often to run the benchmark, and I just want to run it often enough so the JIT will kick in. So I'm just going to run this int loop 5 times. I'm going to open the method in a second to compare to what we're seeing in the JIT log. So run this int loop, and kind of there's the milliseconds and the confidence interval, and I can open up and an auto log here, and open up the log that I just made. And what you get is this debug output from the JIT, and I can look for bench. Did I run int loop? Yeah. And so there's the RPython so Cog uses pretty much what is just method JIT, fairly simple without much inlining right now, but System is going to work for that. Towards that, and RPython is the other extreme. It uses a tracing JIT, which doesn't JIT entire methods. It only JITs inside loop. It JITs one particular trace of execution that it observed. So it does aggressively inline everything it sees in that trace of execution, but it never JITs branches. It will only JIT exactly one trace of execution. And this can be very good for some benchmarks, but very bad for others. And what happens is then you get these loops. And here this is a loop that is inside the method bench int loop. So this is not the JIT code for the entire method bench int loop, it's just one of the loops in there. And it actually says here it's starting at this bytecode. And let's see. And kind of basically it's just this loop in here. It's just kind of adding up those numbers, counting down those numbers. And what you then see is that every loop after JITting it on RSqueak, the first loop iteration will have a lot of assembler, and then it tries to pull out as much as possible of the computation into the first loop iteration, once the loop first, and before the loop proper then is executed. And then there's a small body of assembler remaining, hopefully a fairly small body of assembler remaining, that represents what happens most of the time. And to find those, there's these labels, and what we see here is the entire code generated for the loop after the first iteration. And the debug merge points aren't assembler, those are for debugging purposes. This is just to show you this is a bytecode that I would have executed, and after that debug merge point it says this is the assembler that, or this is the intermediate representation for the assembler that I now generated for this particular bytecode. So what it means if we have 4 debug merge points in a row, it means these bytecodes, like these first 3 bytecodes, I didn't have to do anything anymore. I could completely optimize those away and just leave that out. So even though, for example, we have boxed integers, in here you actually only ever see direct integer operations and no boxing at all, because it knows that inside the loop it doesn't have to box and unbox the integers all the time. It optimizes that away, and then will only after exiting the loop will it create a new boxed integers and plug the result back into that. And due to time, I wanted to show one more thing now. Yes. So I wanted to show what happens in the big bit loop a little bit. So here, I remember I had the breakpoint in the graph port copy bits thing, where I then jumped to the simulate primitive. We can see here somewhere in the JIT code references to this method where it tries to go into a primitive, cannot find the primitive, looks for the VM maker method, simulate primitive with args, and finds it, and then it starts simulating the primitive. And what's cool here is that while the simulation setup is actually fairly difficult, it has to kind of, you generate an interpreter proxy, so it creates a new object, supposedly initializes the interpreter proxy, creates new order collections in the interpreter proxy, and all that stuff. Really, most of that is all optimized away. So many applications still don't happen, and the reason why we even get to being only 20 times slower than the C plugin is because there's in these kind of traces, there's these huge lists of debug merge points where everything is just completely removed, and for many of the bit traces, you're really not doing anything anymore. So this is one of the reasons we think that something like Sister can have huge performance benefits also for Cog of that order of magnitude, where you're completely removing lots of the stuff that you're never going to use. And you can then start thinking about actually moving stuff that used to be in the C land and in slang and in kind of low-level code. You can move that into proper Smalltalk code and use like the proper tools to develop that and rely on the JIT to optimize that for you. And I said we don't have the Bitlit and Balloon plugins. We also don't have large integer plugin, for example. We don't have float plugins. We do all that through the JIT and still get reasonable performance out of this. One more thing I wanted to show. Yeah. So one last thing before we go. So I wanted to just leave you with an impression so we're all Smalltalkers, and I do prefer the Squeak environment or Pharo for VM development, because just the tools are so much nicer than being in Emacs and using command line tools of Python. But one thing that I do like in RPython as compared to slang is that I can use meta stuff like this to define primitives. So here, all the primitives for booleans, I simply say, okay, here's some primitive indexes. These are the Boolean primitive indexes, and then I map them in a dictionary here to the operators in Python for those same Boolean operations, and then I just generate the primitive functions by saying, okay, go over all of these pairs, and then create a function that just is, when you see this primitive index, do this Python operation. And you can use this kind of meta programming to really like shrink down the code. And right now, no, I haven't got built. Right now we're at about like 10,000 lines of code compared to Cog. So that's including like all the JIT annotations and all that stuff, compared to Cog, where the slang code, just because it has to be so close to C semantics and some things have to be so much more explicit, just blows up to about like 5 times that size. And it's for us, for introducing students that have never done VM development before and that have often little experience with low-level C facilities, this is a much, for many of them it's a much smoother way to get into this entire thing, because they can still kind of use object-oriented principles and use some amount of meta programming in the VM and play with this in interpreter. Yeah, that's just, I wanted to leave you with this as kind of the comparison for where I would hope that slang could move towards, to be much more object-oriented, but also at the same time, I would hope that we move to a point where we can get rid of lots of slang, but anyway, just move all that into Smalltalk and then just have Sister optimize all that away. Yeah, thanks.
Tim, I'm having a little bit of difficulty visualizing how it optimizes send. Presumably, sends are Python applications, so there's special code in tracing applications. Is that true?
So you mean sense on the Smalltalk level?
Yeah. So you've got, say you've got a polymorphic send, like the send of initialize inside you, right? Self-facing initialize.
Yeah.
Because the tracing JIT can't turn that into straightforward true trace.
What the tracing JIT does, so this is the send selector micro that we're using, and what we have here is we say, give me the shadow, so our representation of your receiver class, and then just do a lookup and give me the compiled method. And due to the way the tracing JIT works, it's just going to insert a guard. In this trace, I'm going to assume the class is never changed, so I don't have to do the lookup ever again. I'm going to assume the class hasn't changed, and then it just says, I'm going to also assume that the compiled method hasn't changed, and then just going to execute what's in the compiled method. So the send, most of the send bytecodes actually go away completely in the traces. The problem with this is, and we can.
So hang on. So in my language, that means that by default, send are translated as like a monomorphic inline hash.
Yes. Yeah, that's by default, and you can see the problem with that, of course, in here in the polymorphy benchmark that we have set up. This is a benchmark where we generate 50 classes that all have the same method, and then we have a loop where one instance of each class is sent the same message to. And what happens is that we have to generate 50 different traces for the entire. For the same loop, and this is why we're so much slower here also than Cog. Yeah, so that kind of code was really bad.
But it's going to get you really fast Richard's benchmark, which has between 4 polymorphisms.
But we do trace the different things, and the guard that checks that the class of the receiver is going to be the same. That's usually pulled up very early. So we check that, the guard fails, and it goes to a different trace. But yeah, as with the pig, this is only fast for so many hops that you have to do. Which is below the threshold where we're still okay. But at some point we just get really, really bad. But for extremely monomorphic stuff like Mandelbrot, it's just blazingly fast. Okay. Okay, thanks. Good luck.